This lesson will start you off on some of the rules for finding derivatives. You should have already had a lesson that gave you the definition of a derivative where you found the derivative using the limit process. I know that you discovered fairly soon that that becomes a rather long and tedious process, but it does help you to understand from the definition exactly what you're finding when you find a derivative. Hopefully, as we look at these rules and apply them, you'll see that finding a derivative can be a fairly simple process in a lot of cases. And even with the more difficult functions, we can find a derivative a lot more easily than we can going back to the formal limit definition. Your first rule says that the derivative of a constant is 0. And it's written in this form. The derivative with respect to x of c is equal to 0, where c is a real number. It doesn't matter what real number c is. We're going to apply that rule and talk a little bit about why that should be the rule without actually going through a formal proof, although it can be proven. Find the derivative of each function. Your first function is y equals 5. Now you might recognize that if you were to graph this function, you would have a horizontal line through y equals 5. Do you recall when we wrote dy dx or y prime that this symbol, of course, standing for the derivative, means that we're finding the instantaneous rate of change of y with respect to x. And of course, we also learned that this rate of change of y with respect to x is exactly the same thing as the definition of a slope, isn't it? What is the slope of a horizontal line everywhere? Well, you might recall that it's 0, isn't it? So it makes sense for us to say that the derivative of this function is 0 because the slope of this function is 0 everywhere on that curve. And so applying the rule, this is a constant. The derivative of the constant is 0. Look at this one, f of x equals 0. So if I'm finding the derivative, I'm going to write this one f prime of x. That's just a real number. Happens to be 0, but it's a real number. It's a constant, and so its derivative is 0. What about this one? G of x equals pi. What is g prime of x? Well, what's pi? We write it down in a Greek letter format, but pi is the constant that's roughly equal to 3.14, isn't it? The value of pi never changes. It's constant. And so that derivative also would be 0. What about this one? Y equals the sine of pi over 4. Well, you might recall from trigonometry, the sine of pi over 4, or 45 degrees, is the square root of 2 over 2. And so what's the derivative? Well, that's a constant, isn't it? The sine of pi over 4 is always square root 2 over 2, that constant. So the derivative would be 0. So it doesn't really matter what form that constant takes. Its derivative is always 0. Our second rule is called the power rule. If n is a rational number, then the derivative with respect to x of x to the n equals n times x to the n minus 1. Now, rational number means that it could be, what, a fraction, perhaps? Okay, we'll come back to that later. But let's concentrate on the rule. If you have a power of x, notice what happens. This exponent that you saw here is now in front of your x. It becomes a coefficient of x. And your exponent on x is now 1 less than the previous exponent. Now we're going to do a few of these problems using this rule, and then I may talk a little bit about why that rule is true. So let's see if we can apply the power rule. Find the derivative of each of these functions. Well, you'll notice here we have x to a power. So to find the derivative, dy dx, or y prime if you prefer to write it that way, remember that the exponent on the original function ended up in front as a coefficient. I sometimes tell my students you bring that down. And then you write your x, and your new exponent here is 1 less than the old one. So if I subtract 1 from that 4, I get a 3. So if I have y equals x to the 4th, the derivative is 4x cubed. Okay, now let's look at this one. F of x equals x to the 2/3 power. Now 2/3 is a rational number, isn't it? So that rule applies. So the 2/3 will come down in front and become a coefficient. We'll write our x, and we'll subtract 1 from this old exponent. Now be careful here. If you subtract 1 from 2/3, you get negative 1/3, don't you? So my new exponent would be negative 1/3. So 2/3 comes down, x, we subtract 1, we get negative 1/3. Now, I usually have my students rewrite this answer using positive exponents, so I would suggest that they drop this down to the denominator. Remember, if you invert a negative power, then it becomes a positive power. So x to the negative 1/3 is like 1 over x to the positive 1/3. And so I would prefer this form. Your instructor may not care if you leave negative exponents. That's up to them. G of x equals the square root of x. Well, you might say, what does that have to do with this power rule? Recall that the square root can be rewritten as a 1/2 power. The square root of x is the same thing as x to the 1/2 power. Again, we've got a rational exponent there. So if we're getting the derivative, then our old exponent will come down as a coefficient, 1/2. Write your x. Subtract 1 from your old exponent. 1/2 minus 1 gives you negative 1/2. And then again, your instructor may be happy there. I would have my students rewrite this as 1 over 2x to the positive 1/2. Okay? Now, be careful on this last one. Y equals 1 over x to the 5th. Now, when you apply your power rule, do you see this x to the n being in the denominator at all? It isn't, is it? It's x to a power. No fraction form there. So, I'm going to rewrite 1 over x to the 5th as x to the negative 5. Then I will apply the power rule. I'm going to write it as y prime this time. The old exponent will come down in front, negative 5 as a coefficient. Write your x. Subtract 1 from this exponent. Now be careful here. You have negative 5. You're subtracting 1. So that would give you negative 6. Then again, I would have my students rewrite this, negative 5 over x to the positive 6. So in each of these cases, we have applied that power rule. Again, this is an important one, so I want to put it back up here. Your old exponent ends up in front as a coefficient. And then you write your x, and you subtract 1 from that old exponent to get your new exponent. Now, I might just tell you a little bit, and I'm just going to use positive whole number exponents here to sort of demonstrate why this thing works. If we have the function y, or f of x, if you prefer that notation, equals x to the n, recall that if we're finding the derivative dy dx or y prime, it's the limit as h approaches 0, f of x plus h minus f of x over h. Some textbooks or your instructor may have used, instead of an h, a delta x and written it like this: x plus delta x minus f of x over delta x. Either of these forms, they're saying the same thing. But let's take a look at that function. I'm going to use the h form here. F of x plus h. I replace x plus h for x. So I'd have x plus h to the n, and then minus f of x would be x to the n. All of this is over h. Now, I can't substitute h equals 0 because I'd get a 0 in the denominator. So I'd have to do the multiplication here. Now, if that were squared, you know, you'd have x squared plus 2xh plus h squared. If it was cubed, you might know how to do that. In general, the thing that you do know is that your first term will be x to whatever this power is, so x to the n. Your second term will have n, whatever this number is, as its coefficient. X will drop down a power, and h will show up. Now, I'm not going to put down the coefficient here. I'm just going to put a little parenthesis. Your next term would drop down another power on x, but h would be squared. You would continue this. I'm running out of room here. until finally you got to h to the n. Then we've got minus x to the n, and then all of this is over h. Notice the x to the n minus x to the n would cancel out. All of these other terms are going to have an h in it. So if you factor that h out, it leaves nx to the n minus 1 plus a coefficient times x to the n minus 2 times, notice there's still an h, plus each of these other ones are going to have h's in them. This is the only one where the h will be completely factored out. After you cancel the h's here, if you substitute a 0 for all these other h's, the only thing left is this. And that's actually where this comes from. Now, your instructor may have done a more formal proof where they put in all of the steps, but this illustrates, going back to the definition of a derivative, why this rule is working as it is. Our next rule is called the constant multiple rule. If f is a differentiable function, that just means we can find its derivative, and c is a real number, then the derivative with respect to x of c times f of x is equal to c times the derivative of the function f of x. In other words, c times f prime of x. If you have a constant times a function, you bring your constant down and you take the derivative of the function. Let's see how that works. Find the derivative of each of these functions. Y equals 6x cubed. This means that I have 6 times the function x cubed, doesn't it? Now, we don't always take the time to rewrite that, but I'm just emphasizing this is a constant times this function. So, according to our rule, to get the derivative, I would simply bring this constant 6 down and multiply that times the derivative of this function. Now, this is a power of x, and we just learned to do the derivative of this power of x. We would bring that old exponent down in front as a coefficient, write our x, subtract 1, we get 3x squared. 6 times 3x squared is 18x squared. So we brought the constant down, we took the derivative of our function, we multiplied those answers, and we have our final derivative. Now, usually, I do these steps together. In other words, as I bring this exponent down as a coefficient, I go ahead and multiply it times whatever constant is there. That just saves having to write this step down. So if we apply that rule here, notice my function says 4 times x to the 1/5 power. So I have a constant times this function. So I would technically bring the constant down, 4, times, take the derivative of the function, 1/5 times x, subtract 1 from 1/5, and you have negative 4/5. To simplify this, 4 times 1/5 is 4/5. So you have 4/5 x to the negative 4/5. And again, I would want my students to write this as 4 over 5 times x to the 4/5, pulling that down so I'd have a positive exponent. But again, I usually will pull the 1/5 down and say 4 times 1/5 is 4/5 rather than writing this step down. Now let's see how we can do this one. I have 7 times the 4th root of x cubed. Well, first of all, let's rewrite the function. This is in radical form. Let's write it using exponents. Recall that the power on x is the numerator of your fractional exponent, and the root you're taking is the denominator. So this is 7 times x to the 3/4 power. The root is the denominator of that fractional exponent. Now we're going to apply our constant times a function rule to get our derivative. If I multiply 3/4 times 7, that's like bringing my constant down and multiplying. 3/4 times 7 gives me 21/4. I'll write my x, subtract 1 from this exponent gives me negative 1/4. And then finally, again, my students I would want to rewrite as 21 over 4x to the 1/4 power. Okay, let's look at this one. Again, I don't have a rule yet that says anything about what to do if I have a fraction form, a division here. So I'm going to rewrite this function as 3 times x to the negative 8. Now don't confuse this with taking a derivative. I'm simply rewriting the function to put it in a form so that it's easy to find the derivative. I have a constant times this function. So my derivative will be this constant times the derivative of this function. And as I said, I'll skip this step and do it together. If I pull the negative 8 down as a coefficient, negative 8 times the 3 gives me negative 24. And then I'll write my x, subtract 1 from my exponent gives me negative 9. And then again, finally, I would want my students to rewrite this using positive exponents. So I would want to see negative 24 over x to the 9th. We have already seen some rules that should make finding derivatives a lot easier. The derivative of any constant is 0. The derivative of a power of x, are you beginning to get that rule? You bring the old exponent down in front as a coefficient, write your x, subtract 1 from that old exponent to get your new exponent. And then finally, if you have a constant times a function of x, your derivative is that same constant multiplied times the derivative of your function. Let's look at some other rules that will help us. This is the sum and difference rule. If f and g are differentiable functions, again that just means we can find the derivative of each of these, then the derivative with respect to x, oops, I shouldn't have that c there, I had a mistype, let me mark that out. This should just be f of x plus g of x in here. I apologize for that typing error. Notice you're adding two functions in here. The derivative of the sum of two functions is equal to the derivative of the first function f plus the derivative of the second function g. I've written it another way. Take the derivative of the first one, we can call it f prime instead of using this notation, plus the derivative g prime. Similar rule applies for a difference. The derivative of f of x minus g of x is the derivative of the first function minus the derivative of the second function, f prime of x minus g prime of x. Let's use that rule. Find the derivative. Y equals 2x cubed plus 5x squared minus 3x plus 2. This is just a polynomial, isn't it? But look, it's this function plus this function minus this function plus this function. It's just a sum and difference of several other functions. So we're going to apply the rule which says I'll take the derivative of this one plus the derivative of this one minus the derivative of this one plus the derivative of this one. Now as we start going through this to get the derivatives, you'll see that we're also going to be using some of the previous rules that we've learned. In other words, look at this function. 2 times x cubed. It's a constant times the function x cubed. So we learned that we do the constant times the derivative of the function. And we do it together. 3 times 2 gives me 6x. I'll subtract 1 from that and get a squared. Now I'm going to add my next derivative. The derivative of this one, again, is a constant times this function. Doing it together, 2 times 5 is a 10. X, notice if you subtract 1 from that exponent, you get a 1. You don't have to write an exponent of 1. Subtract. I still have a constant times a function of x. So I'll bring down the 3. Now follow me on this one. Your old exponent is a 1. Bring it down. Write your x, subtract 1 from that, and you get a 0 exponent. Okay? I'll come back and simplify that in a second. Finally, plus the derivative of a constant is 0. Now let's take a look at this. Anything to the 0 power is 1, isn't it? So this is just 1 times 1. So simplifying this, I have 6x squared plus 10x minus 3. I don't have to write the plus 0. The derivative of x ends up being 1. X to the 1 using your power. 1 comes down, you write your x, subtract 1, you get to the 0, and that's just a 1. Okay? Alright, let's look at this function. Again, I've got this minus this plus this minus this. So it's a sum and difference of several functions. And so I will be using that rule to get the derivatives. So first of all, I'm going to rewrite my original function. So let's just put an equal here. This is not in a form to find the derivative yet. So what I'm going to do is I'm going to pull this up, just the x part, to write it as a power of x. 3/4 x to the negative 2. Okay? Subtract. Now I'm going to do a similar thing here. I'm going to pull this up and write it as a negative power. 6x to the negative 1. Now the rest of my function is in a good form to find the derivative. So again, don't be confused about when I'm finding the derivative. This is simply rewriting the original function so it's in a form that I can find the derivative. Okay, let's get the derivative. F prime of x. Negative 2 will come down and multiply times 3/4, and I'll get negative 3/2. You might think negative 6/4 and then reduce it. Write your x, subtract 1, you get negative 3. Okay? We'll move to the next term. Now I'm going to kind of do this together. When I pull this down, it's going to give me a negative 6 minus a negative 6 will be a plus 6. Write your x, subtract 1, you get negative 2. Plus the derivative of x is 1, and then minus 0. Now I'm putting these zeros in for emphasis here for you. You don't have to write those zeros at all. And of course we will rewrite this without the 0. But I want to emphasize again, we brought the exponent down, we multiplied times whatever coefficient is already there using the constant times a function rule. Wrote our x, subtracted 1. Here, when I bring this down, that negative 1 times this is going to change that sign to a plus. So I usually just think negative 1 times negative 6 is a positive 6, x to the negative 2. Now I would want my students again to rewrite this. So we're going to do 3 over 2x cubed, dropping that back under, plus 6 over x squared plus 1, and again you don't have to write the 0. Now keep in mind on this, because I sometimes have students make mistakes, only the x has that negative 2 power, so only the x goes under. 6 is to the first power here. Okay, let's look at trig functions. The derivative with respect to x of sine x is equal to the cosine of x. And the derivative with respect to x of the cosine of x is equal to the negative of sine x. Now I'm not going to prove these rules for you here. We're simply going to use them. I would expect that your instructor will probably show that to you. I might just remind you that if you wanted to prove it, what you'd have to do is say, if you're using the function f of x equals sine x, to get the derivative, dy dx or f prime, however you want to write that, you would have to go back to forgot to write the limit. Limit h approaches 0, f of x plus h minus f of x all divided by h. Here's what this one would look like. You would have the sine of x plus h minus the sine of x all divided by h. Now I might just tell you, use an identity to rewrite this, and some things will change. You'll be able to do some factoring and such. And then you have to also apply to a special trig limit that you might have looked at when you learn to evaluate limits. At any rate, if you do this out and simplify it, you'll prove that the derivative of the sine function, sine x, is equal to cosine x. Now, you need to commit these to memory. The derivative with respect to x of sine x is cosine x. The derivative with respect to x of cosine x is negative sine x. It's usually easy to remember sort of that they go to the other function. Just remember which one has that negative on there. Let's see how we can use this rule. Find the derivative of each function. Y equals 5 times the sine of x minus 2 times the cosine of x. Now, again, see this minus sign right here? I have this function, subtract this function. So we're going to use the rule that says take the derivative of this one minus the derivative of this one. And on this first one, 5 times the sine of x means I have a constant times this function. So we'll use the rule that says if you have a constant times a function, you multiply the constant times the derivative of the function. Okay, so let's get y prime here. I have a constant times sine x, so I'm going to bring that constant down and multiply times the derivative of this sine x. Well, the derivative of sine x is cosine x. Subtract, I have a constant times this function. I'm going to bring the constant down, times the derivative of this function. The derivative of cosine is negative sine x. Now, I caution you, be sure and use these parentheses to indicate that you're multiplying the constant times the derivative of the function. Otherwise, this looks like minus 2 subtract sine x, which is incorrect. We're going to simplify our answer. We have 5 times the cosine of x, and minus 2 times negative 1 sine x gives a positive 2 times the sine of x. Okay? F of x equals x plus the cosine of x divided by 3. Before we find the derivative, let me rewrite this just slightly. This is the same thing as saying 1/3 times the cosine of x, isn't it? Do you see that? So having rewritten the function in that form, then we can get the derivative. The first function is x. The derivative of that is 1. And then we're going to add. I have a constant times this function. Bring the constant down. Times the derivative of cosine is negative sine x. And again, we'll finally simplify. 1 minus 1/3 times the sine of x. Now, these are all the basic rules that we're going to look at in this lesson. But in the next problems, we're going to sort of see how these rules can fit together. We'll use them kind of in a mixed example set. And then we're also going to look at some applied problems using this new stuff that we've learned. Find the derivative of each of these functions. Now, I have chosen these to talk a little bit about how to rewrite correctly and to be careful with these things. Notice on this one, I have the quantity 2x to the 4th. So the first thing I'm going to do is I'm going to rewrite that. 2 to the 4th is 16. So that's the same thing as saying 3 over 16x to the 4th. Okay? Plus, I have 8 over 5x to the negative 2. Now, my negative power is down here. Remember, though, if you flip it, then the power becomes positive. So it's just the x that has this negative power. So if I flip it, it's going to end up here. And so I'm going to have 8x to the positive 2 over 5. And then finally, I'm going to rewrite this last as 4 over x to the 1/2 power, because the square root is a 1/2. Now, I'm still not quite through rewriting, so I'm still not ready to find the derivative. These powers of x that are down here in the denominator need to be brought up. 3/16 x to the negative 4 plus, I'm going to write this as 8/5 x squared minus 4x to the negative 1/2. Again, all I've done so far is rewrite the original function into a form where it'll be easier to find the derivative. Now we're ready for the derivative. Constant times this, so we'll bring that exponent down. Negative 4 times 3/16 is going to give me a negative 3/4. Write your x, subtract 1 from that exponent, you get negative 5. Plus, 2 is going to come down. 2 times 8/5 is 16/5. Subtract 1 and you get x to the 1st power. When you bring this negative exponent down, it's going to multiply times that negative 4, make a positive 2. X, subtract 1 from negative 1/2, you get negative 3/2. Did you follow all that? Negative 1/2 times negative 4 is positive 2. Write your x, subtract 1 from negative 1/2. Negative 1/2 minus 2/2, if you will, is negative 3/2. And then again, I would want to rewrite this with positive exponents. So negative 3 over 4x to the 5th. And if you want to write 16x over 5, that's fine, or 16/5 x, either one. And then finally plus 2 over x to the 3/2. It was really almost more work to rewrite the original function than to take the derivative, wasn't it? Okay, let's look at our second one here. F of x equals 5 pi x plus 2 times the sine of x. And we want the derivative. Now, keep in mind here, some students get confused because that looks like a letter, sort of. It's not a variable. Pi, remember, is a constant. 5 pi means 5 times pi, about 3.14. So that's a little more than 15 here we're talking about. But at any rate, we have this constant times our x. So we bring down our constant, 5 pi. The derivative of x is 1. I'm going to put that down for emphasis. Plus, bring down our constant, 2 times the derivative of sine x is cosine x. I'll just rewrite this without that 1 in there. 5 pi plus 2 times the cosine of x would be my derivative. Don't confuse, by the way, when you have a constant times a function versus just a constant by itself. Remember, the derivative of a constant by itself is 0. But if you have a constant times a function, the derivative is that constant times the derivative of the function. There you don't get 0. Okay, well, let's look at an applied problem here. Find the slope of the graph of f of x equals 3 sine x at the point pi over 2, 3. And then what is the equation of the tangent line there? Well, recall that we get the slope of a graph from the derivative, don't we? So if f of x equals 3 sine x, let's take the derivative, f prime of x. You have a constant times this function, so your derivative is the constant times the derivative of sine is cosine x. I guess I didn't really need that parenthesis, but I put it in for emphasis. My derivative is 3 times the cosine of x. Remember, this basically is a formula for slope of the graph at any point. We want to know the slope at this point. So my slope, m, is going to be 3 times the cosine, what's x? Pi over 2. 3 times the cosine of pi over 2. Well, the cosine of pi over 2 is 0. So 3 times 0 is 0. My slope is 0. What does that tell you? It tells you have a horizontal tangent line, doesn't it? So your equation, and if you didn't catch that it's horizontal, if you do, you can write the equation real easy. But if we go back to our point slope, y minus y1 equals m times x minus x1, I have y minus 3 equals my slope of 0 times x minus pi over 2. Y minus 3 equals 0, because 0 times anything is 0, or y equals 3. Now, if you caught right here that this is going to be a horizontal tangent line, you might know how to write that equation without going through all of this. It's a horizontal line through this point, so it has to be y equal 3. A rock is thrown from the top of a building 48 feet high. The position of the rock is given by S of t equals negative 16t squared plus 32t plus 48, where S is measured in feet and time in seconds. The first question wants to know, when does the rock hit the ground? And the second is, what is the velocity of the rock at impact? In other words, when it hits the ground. Okay, now S gives me position. So you have to realize, if the rock hits the ground, the position of the rock would be at 0 feet. It's on the ground. So the position S is 0 equals negative 16t squared plus 32t plus 48. Position is 0. And we're going to solve this for t and find out when that happens. Now I noticed that 16, 32, and 48 all have a common factor of 16. I'm sorry, not 16, of 4. I guess 8, don't they? Let's do 8. They do have 16, don't they? I'll get this right in a minute. Let's factor out negative 16, okay? T squared, I'll get this right, minus 2 times t. 2 times 16 is 32, okay? And then minus, what, 3? Okay? So negative 16t squared plus 32t plus 48. See, that just goes to show you that all of us get kind of mentally blocked every once in a while. Okay, we can factor this. T minus 3, t plus 1. Okay? If we set each factor equal to 0, we'll get t equal 3 or t equal negative 1. I'll rule that one out since we're talking time here and we can't go back in time, not negative. So we will hit the ground 3 seconds after we throw it. Okay? So 3 seconds later we hit the ground. The second question, what is the velocity at impact? Recall when you learned about a derivative, if I find ds dt, I'm getting the instantaneous rate of change of s with respect to t. Position with respect to time, rate of change, position with respect to time is velocity, isn't it? So the velocity can be found by taking the derivative of my position equation. So applying our rules here, the derivative of this first one will bring the 2 down. I'll get a negative 32t to the first power. Notice when you subtract 1 from that exponent. Plus, I'll bring down the constant 32. The derivative of t will be 1. And finally, the derivative of this constant right here is a 0. So my velocity is negative 32t plus 32. I wanted to know the velocity at impact. I hit the ground when time was 3 seconds. So my velocity will be negative 32 times my time of 3 seconds plus 32. This gives me negative 96 plus 32. And let's see, I'm going to get a negative 64 here, right? This is in feet per second. Now, if you haven't already discovered this from your first lesson when you studied velocity, why is this velocity negative? Because we were going in the negative direction. Okay? We threw the rock and it's going down, which we're considering our negative direction here. So we hit the ground at 64 feet per second and we were going in the negative direction. This completes our lesson on using these basic rules for finding the derivative. I hope that you see how you can use these derivatives, find them much easier than going to that limit definition, obviously. But then keep in mind what you're finding is an instantaneous rate of change. So after you find your derivative, you have a formula for that instantaneous rate of change, which you can apply to being slope of a graph or being velocity or many other applications. This completes our lesson.